Hi everyone, good morning and welcome back. So this is another data analysis video as normal. I am kind of using Jupyter Notebooks. I'm working using Python and I'm still recording a series of videos about probability distributions. In this particular video, I'm going to focus on the binomial distribution and I'll kind of demonstrate how to manually calculate the probability mass function, the PMF, the binomial, and also the CDF, the cumulative density distribution function. Okay, so the binomial probability model has a wide range of uses in the real world. It's usually associated with situations where you've got two outcomes frequently labeled as success or failure. So like the classic example of this is a coin flip. Does the coin come up heads or not type of thing. But it doesn't have to be just toy examples like that. So research often involves quantifying the probability that an event occurs. So the percentage of successes in a population, or the likelihood of certain outcomes that can be classed as kind of success or failure. And this success and failure can be value neutral in the sense that does it happen or does it not, essentially. So as we saw when I was kind of outlining the normal distribution, the Gaussian model, each probability model has its own set of properties and parameters. And in order for a random variable to be considered to have the properties or characteristics of a binomial distribution, it must meet a number of conditions. And these are that it's a random process with a fixed number of trials, usually labeled as n, and the outcome of each trial can be classed as success or failure. So for example, if we flip a coin, did it come up as a head or not? The probability of success, P, is the same for each trial. So there's a success probability for each event, for each trial, and that's the idea is that that's fixed essentially. So usually with a fair coin, we flip it, and the probability of success of something coming up heads we'd assume to be usually about 50%, 0.5, yeah. And lastly, that trials should be independent, so the outcome of one trial does not influence the result of the next. So if we flip a coin once and it comes up heads, that's not going to influence the result if we flip it again and it comes up heads. And what I will do in this video is I'll demonstrate how to simulate some data and variables that follow the binomial distribution, or what I'll do that in this series of videos essentially. But what I'll specifically do in this video is I'll show how to calculate the binomial manually, and then show how to obtain kind of probabilities for given values of kind of given number of successes for a certain number of trials. So if we had 3 successes in 10 trials, we'll be able to use the PMF and CDF to sort of work those things out. So to calculate the binomial manually, so because it can only take on discrete values, so like 1 success, 2 successes, that type of thing, the binomial distribution has a probability mass function, or PMF. So it's a discrete distribution. It can only take on certain values, success and failure, and it cannot take on continuous real number values. So the PMF for the binomial is based on k number of successes in n trials with a probability p of success on each trial. So those conditions we just kind of discussed above there, essentially. So the PMF for a random variable x for that is binomially distributed is this essentially, and what this is saying is that for a random variable to be distributed binomially, we've got this first kind of this first term here, n, with a superscript c and an x. That's n choose x essentially. I'll say a little bit more. That's the binomial coefficient. I'll say a little bit more about that in a second. Times p to the x times 1 minus p to the n minus x. So in this case, well, n is the number of trials and x is the number of successes, as opposed to previously it said k. That's quite common notation, n choose k. Here we're using just n choose x essentially. So although my markdown formatting is not particularly good here, it looks like this is x times p. It's not. That's kind of it's n choose x times p essentially, times 1 minus p to the n minus x. That's kind of the PMF for a binomial random variable. And this first kind of element of it, n choose x, is referred to as the binomial coefficient. So what this means is from n trials, choose x number of successes. And calculating this coefficient makes use of the factorial operator, where whatever specified number you have is multiplied by all preceding lower values. So underneath here is the formula for the binomial coefficient. So this here is another way is the actual formula for this. It's another way of stating that. So that's n factorial, these sort of exclamation mark looking characters are kind of factorial operators. So that's m factorial divided by x factorial times n minus x factorial. Okay, so what we're going to do is first we will work out how to calculate the factorial of a number, and then we create a function that allows us to calculate the binomial coefficient. And then what we'll do is we'll kind of plug that in here and create a function that allows us to work out the PMF, the probability mass function for a binomial distribution. And then we'll need the PMF in order to work out the CDF, the cumulative distribution function. But the first thing we need to do really to be able to work this out is calculate the factorial of a number, so this factorial operator. So if we're calculating this binomial distribution manually, the PMF for it, without using any software libraries, which is what I'm doing in this particular video, what we need to do is calculate the binomial coefficient here first. And unfortunately, the kind of Python core and base doesn't have a factorial operator. So what we need to do is define some sort of function that performs that kind of factorial calculation. And that's what I'm doing here in this first cell. So I'm basically defining a function called factorial that takes a value x, and it's then I'm stating f is 1, and then I'm using a for loop for I in range x, whatever x value we put here. F is going to be f times I plus 1, and then we'll return f. So essentially what this will do is, let me run that particular. So we've created that function. We can now call this function by using this name and specifying a value. Essentially, what this is doing is it's working out the factorial, but it's sort of doing it in a reverse way to how the factorial really works, I guess. So we can test this function factorial by giving it a value. So we can just put some arbitrary number in, like 3. So factorial, I'm now calling the function we created, factorial, putting the number 3 in. And the calculation that if it works correctly, the calculation that it will do is whatever value we put in 3, it'll do that times every preceding lower number. So 3 times 2 times 1, which will return a value of 6, which is correct. What this function is actually doing here is sort of doing the opposite. It's doing like because we're setting f to 1 to start with, and then when we iterate through, we're adding 1 to each value of I in the range of x. Yeah, so it's going up to 3. So what it's really doing is 1 times 2 times 3, but it's still, because multiplication is commutative, it's still returning this at the correct value. So we've now got a function that returns the factorial of a number. Okay, so Same here, let's try this, but we'll just a couple of other examples. If we put 4 in, 4 times 3 times 2 times 1 should return a value of 24. It does, thankfully. And then let's put 8 factorial in. So 8 factorial should be 8 times 7 times 6 times 5, 4 times 4 times 3 times 2 times 1. And this should return a value of 40,320. Okay, so it has worked, that's good. So we've got a function that we can use for our factorial. There is another way to do it as well. I'm just going to demonstrate this. We're probably just going to use this simple factorial function when we calculate the binomial coefficient and the PMF, but we can also use recursion as an alternative method to calculate the factorial of a number. So I'm doing exactly the same. So I'm going to define a new function, factorial underscore v2 version 2, which it's a function that does exactly the same thing as factorial, but we've coded in a slightly different way here. So what we're saying is we put some value of x in. If x is exactly equal to return 1, it's just going to return 1. If it's not, it's going to return whatever value of x is times factorial version 2 minus 1. So it's going to kind of loop through, and this is kind of how we naturally think of a factorial type of calculation, essentially. So we can see if this works in the same way as above with like some arbitrary numbers. So let's put 3 into this new function we just created. So it returns 6, that's correct. 24, and yeah, 40,320. All right. So we've now got we've got 2 functions that we can use to calculate the factorial of a number. That's useful because we're going to need it we're going to need to plug this in to this particular formula. So let's do that. Let's calculate the binomial coefficient. So we can make use of the factorial function we created above as part of a function that gives us the binomial coefficient. So here, the function that we're going to define for the binomial coefficient is going to take 2 values as arguments. The first is the number of trials n here, and the second is the number of successes x. I'm using x rather than k essentially, but I'm kind of using k in some of my notation. So here we're defining a function that gives us the binomial coefficient for n choose k. So we're defining binomial coefficient. The arguments are n and k, how many trials, how many successes. And to calculate that, I'm just creating an object, and that takes our factorial function and feeds it into this formula. So n factorial divided by x factorial times n minus x factorial. Okay, so hopefully you can see that. So this formula here is the binomial coefficient formula. So we're taking factorial of n divided by the factorial of x times the factorial of n minus x, and then we're going to return the object. I've just given it an arbitrary name there. So we've now got a function that defines our binomial coefficient. Okay, so we can test this using some arbitrary choice. So for example, if we had 10 trials and 2 successes, we can call binomial coef and specify 10 trials and 2 successes. And we'll see we've got about 45% probability of 2 successes in 10 trials, following that kind of binomial distribution. Okay, so a couple of things we've done so far. We've calculated that, we've created a function to create the factorial, to work out a factorial of a number. We've used that function inside a formula for another function to create the binomial coefficient. Remember, that is this, which is the first part of our formula for the PMF, the probability mass function. What we're going to do next is use this, substitute the function we created for the binomial coefficient here, and multiply it by the rest of the PMF formula to create the PMF, probability mass function, for a binomial distribution. So to do that, to obtain the PMF, we're going to define a function. So we're doing this all manually. We're going to define a function that takes arguments for the number of trials, n, the number of successes, x, and the probability of success on each trial. So it's taking 3 arguments. So we're going to define a function, def. We're going to call it binom underscore PMF. And the arguments are n, x, and p. So n trials, x successes, p probabilities. Okay, and hopefully you can see what we're doing here. It's them saying return. The value it's going to return is basically going to. It's going to be all of that PMF formula, but n choose x is going to be replaced by this, which we've created a function for. Okay, so let's see how that works. You can see here we're defining this, and we're going to return. The value we're going to return is going to be our binomial coefficient function, where we're specifying n and x, times p to the x times 1 minus p to the n minus x. So these double asterisk operators are exponents raising to the power of. And you should be able to see here that all this is essentially this formula here. It is exactly that formula there. Okay, so let's run that. So we've now got a function that we've created, we've defined, that gives us the probability mass function for binomial distribution. And we can test that. We can test the binomial PMF function using kind of arbitrary values. So let's say we specify we want 10 trials, so 10 coin flips, 10 trials, whatever they are. And from those, we want 4 successes. So we've got an x value equal to 4, and a probability of success on each trial of 0.3, so about 30%. So all I'm doing here is calling our new function, binom PMF, 10 trials, 4 successes, 30%, 0.3 probability of success. So if we run that, what we can see is the probability of 4 successes from 10 trials with a success probability per trial of 0.3 is about 0.2 or 20%. Okay, is what we can interpret that as. So if we've got a variable that follows a binomial distribution, and we kind of collect data on that variable, and there's a success we know the success probability for each trial is about 30%. And we observe for, there's a 20% chance we will observe at least, we'll observe four successes from just 10 trials. Okay, so we've got the PMF, and we can use that to obtain the cumulative density function, the cumulative distribution function, that should be, I believe. So the binomial CDF, cumulative distribution function, it tells us the probability of some number of successes x or less from n trials. So I've talked about the CDF before, and it's the cumulative probability. So we read values from it. If we give it some x, it will tell us what the probability is, the cumulative probability is of getting that value or lower. Okay, and we can work out the probability of getting that value or higher by taking 1 minus the kind of CDF probability. So to calculate the CDF for the binomial, we make use of the probability mass function, that function we've just created. So one difference is that the formula set for the CDF makes use of a floor operator. So a floor operator rounds a floating point decimal number towards 0. So if it's positive, it'll round it down towards 0, and if it's a negative floating point decimal, it'll round it away from 0. Okay, so it rounds it down to the kind of next smallest integer value. Okay, so this fits with the usage of the CDF because it tells us the probability. We use the CDF if we want to know the probability of a value of x or lower. Okay, so first of all, what I'm going to do is define a function that carries out floor operation by rounding down. So what this function here does, I've called it floor op, is it takes positive values of x, rounds them down to the nearest integer, and it takes negative values of x and rounds them down to the next smallest, I should say, integer. So it rounds them away from 0. So I'm defining floor operator. We feed it some value x, and if x is greater than or equal to 0, then f equals the integer of x, so it basically rounds it. Else if f is equal to integer x minus 1, return f. So what this is going to do, if it works correctly, is if we give it a positive value of x of 5.7, we should see this round down to 5 essentially, and it has. And if we give it some negative value of x, so here we're going to give it negative 3.4, and we should see this round down to the next smallest integer away from 0, so it should return negative 4. Okay, has done. Seems to be working okay, our floor operator. We're going to, only reason we've created this, like we did with the factorial, is we're going to need it in to work out the CDF. Okay, so with that function for the floor operator, we can now incorporate into a function that gives us the binomial CDF. So let's define a function called binomial CDF. It's going to take n, x, and p, so number of trials, number of successes, probability of success as its arguments. And then we're specifying initial value for p-val. So p-val equals 0. So this is the probability we want it to return given our parameters. And then we're making use of our floor operator here. So x floor equals floor operator on whatever our number of successes is. So whatever we put in, it's going to round it down to the next smallest integer. And then we're using a for loop for I in range x floor plus 1, so the next value up. It returns a p-val equal to p-val plus binom underscore PMF. So it's going to take our binomial PMF function and use that to calculate the p-value. So let me run this and we'll kind of demonstrate it. Hopefully it'll make a little bit more sense. So let's now call this let's use, like use the CDF to work out the probability of something. So we're going to call binom CDF, and we're going to say, as we did above, we're going to say we want 10 trials, 4 successes, and a success probability of 0.3. Now remember, it's not returning the same thing. It's not returning the exact probability of getting 4 from 10 with a 0.3 probability. What this is returning is the probability of getting 4 or less in 10 trials when the success probability is 0.3. And you can see what we get is if we round this up, it's 0.84973, etc. If we round this to 2 decimal places, we can be using the CDF for the binomial distribution. We get the probability of getting 4 successes or less, 4 successes or fewer from 10 trials when the success probability is 30%, is 0.3. On each trial is about 85%, so it's 0.85. Okay, so an 85% chance of seeing 4 successes or less on trials with a specified success probability of 30%. We'd obviously play around with these, but what I've done in this video is kind of demonstrate to try build a bit of intuition around the binomial distribution, and also just to sort of demystify stuff like this a little bit. These kind of, the formula for the probability mass function, what the binomial coefficient actually means, things like that. We've broken it down and done it manually without using any software libraries, just using kind of base Python software that's available. Hopefully that was helpful. I'm going to make a couple more videos using about the binomial distribution, where I'll use the math library and SciPy library. Everything we've done here you can do like really quickly and easily in using SciPy, using the stats functions, that library from SciPy. So you kind of wouldn't need to do this, but the purpose of this video was kind of to sort of improve our understanding of, well, what is it we're doing when we're working out probabilities for a variable that follows a binomial distribution. So a couple more videos about the binomial, and including I'll also do one where I'll simulate some data that follows a binomial distribution. I'm just going to change that because I can see there's an error and it's bugging me. All right, hopefully this was useful and interesting. Thanks for watching and listening, and I shall see you soon.